Hey, good afternoon. This is Professor Lemieux, and back by popular demand, I'm coming back with a new screen capture video. Today's screen capture video is about Reynolds transport theorem and the derivation of the conservation of mass, and a great example to follow it. So let's start right off with Reynolds transport theorem, or a recap of what we know about it so far. In class, recently we derived 3 different versions of it. I'm going to recap them right here so that we have them for us. The restricted form of Reynolds transport theorem tells us that ddt of some extensive property of a system that's in the Lagrangian frame of reference is equal to ddt of the integral over the whole control volume corresponding to the system of rho intensive B dV minus the flux of material entering the control system if we have one opening plus the flux of stuff leaving, fluids leaving the control system if we have one exit, assuming that the properties are uniform across both the inlet and the outlet. The velocity is perpendicular to the area at the inlet and at the outlet. And thirdly, there's only one inlet and only one outlet. Okay, so quite restrictive, but as we saw, it comes in a nice, convenient form. And I'm calling this RTT restricted, Reynolds transport theorem restricted, or form number 1. The second form that we derived in the handout in the previous class is where we have more than just one inlet, one outlet. And your handout kind of goes into a little bit more details on that. What happens then? Well, then the derivative of the extensive property over the system B is equal to the same first term as before. So the rate of change of the material that's already present inside the control volume that matches that system at time t equals 0, minus the sum of everything that goes in to that system, because we now have more than one opening, plus the sum of everything that goes out of the control volume, because again we have more than one opening. And that's form number 2. I'm going to box them to make them look all pretty here. Let's do that quickly. Oops, what's going on here? I don't know what's going on. Let's try again. Okay. Alright, and this one here is RTT number 2, and it has the same 2 caveats as the previous one, so I'm just going to copy them here quickly so we know what we've got here. That's what we assume. And this is what this one, this is what this one assumes. Okay. Finally, the general form of the Reynolds transport theorem is really the one that we want to make a big effort to understand and be able to use going forward. What it tells us is that the rate of change of the extensive property B over the system is equal, again, to the unsteady part of what's going on in our arbitrary control volume in this sense, in this case. So the very same first term as we had in the previous 2 representation of the RTT. But instead of having fixed inlets and outlets where the flow props are uniform and the velocity is perpendicular to the area, in the general form, we integrate over the entire area of the control volume, and we are looking at the flux of properties across the boundaries of that control volume, and we take into account the fact that the velocity may not be aligned exactly with the normal to the surface of the control volume, hence this dot product that we've got over here that takes care of that. This is the very general form of Reynolds transport theorem. When we don't use any qualifier, this is what we mean when we say Reynolds transport theorem. So there is no assumptions on which this is based. The properties don't have to be uniform. The velocity doesn't have to be perpendicular to any sections of the area. All it's doing, it relates the rate of change of the Lagrangian representation of a system, so when we track the mass of fixed particles, to a fixed region in space, a control volume approach. This is what this is telling us, regardless of what the fluid properties specifically are doing on their own. So let's look at the physical representation of this theorem. What does each term mean? It's more than just a mathematical construct here. Each of the term means something very specific that we need to understand in order to appreciate this. So the very first term, d dt of b cis, represents the rate of change of any arbitrary extensive, it's key here because we need to be able to add it up, extensive property of the system. Okay, that's what we're tracking. We're tracking the system. So that means we're in the Lagrangian frame here. Or the system frame of reference. The first term on the right hand side, this guy right here, is really the same thing for the control volume. So really I can say that this is what this says, and of course those two expressions are equivalent, and they represent, either one of them represents the time rate of change of what's inside the control volume. So it's the same extensive property within the control volume. And the integral itself, this part right there, represents the total amount of the extensive parameter that's contained within the control volume. So that part is the B sub CV, which you can gather just by looking at the equivalent expression. Okay, so that leaves us with that third term. Here, why don't I give them numbers here to keep track of what we're looking at. 1, 2, 3. The second term on the right hand side gives us the integral. So 1, 2, 3 terms. That third term gives us the integral over the control surface, which I've also called area of the control volume. That's just the control surface. It's what wraps the control volume, of the intensive property times the penetration of fluid within the boundaries of the control volume. So that represents the net rate of flux. Flux or flow rate you can think as, of our arbitrary extensive property through the entire control volume. Okay. So the negative sign in terms 3 is because the dot product is always negative when V goes inside the control volume, because by definition N is defined as being positive, pointing outward from any area element of the control volume. So when we want to add the stuff going in as being positive, we have to take the negative of the dot product. That's what that is all about. So that takes us to the conservation of mass now. Once we have these expressions for a Reynolds transport theorem, we can apply that to conservation of mass to derive a useful expression for conservation of mass. Okay, what does it say? Well, really, the only thing we need to do to our Reynolds transport theorem is define our arbitrary property B_cis. What's it going to be for conservation of mass? Well, the property that we're interested in tracking in conservation of mass, of course, is mass. So let B of the system, the extensive properties of the system, be the mass of the system. So therefore, little b, which is the intensive property corresponding to capital B sub cis, is defined as the extensive property per unit mass. So that's going to be equal to mass over mass. It's simply going to be 1. Little b is simply going to be 1. Okay, so we're in good shape then to plug that into the general form. Let's start with the general form of Reynolds transport theorem. That's going to tell us that the derivative with respect to time of B_cis, right? That's what the left-hand side says, which now becomes derivative with respect to time of the mass of the system, is equal to term 2, the first term on the right-hand side, which is d dt of the integral over the control volume now of rho times little b times dv plus the integral over the area of the control volume of rho times little b times v dot n dA. But b little b, as we saw, is equal to 1. So therefore, our theorem tells us that this is equal to d dt of the integral over the control volume of rho dv plus the integral over the area of the control volume, the control surface, of rho v dot n dA. That makes sense, right? Because this is the mass of the control volume. That's what we want. And this is actually the flux of mass into the net flux of mass into the control surface, the control volume through the control surface. Okay. All right. So we know that in general, conservation of mass tells us that this rate of change is equal to 0. So therefore, this rate of change right here must also be equal to 0. And voila, that is our statement of conservation of mass from Reynolds transport theorem for a control volume. We've got that d dt of the integral of the control volume of rho dv plus the integral over the control surface of that same control volume of rho v dot n dA must be equal to 0. Conservation of mass all wrapped up. Okay. All right, very quickly, let's look at the general cases when we, the flow is steady. We have one inlet, one outlet, and we have uniform properties across both the inlet and outlet. Notice that we're not saying that the density is constant everywhere in the system. We're just saying that the density is constant across the opening and it's constant across the outlet. Could be different in both cases, but it's just constant. So what does that mean in terms of our main equation here? Let me call that equation 1. Well, that means because it's steady, that ddt over the control volume of rho dV must be equal to 0. That's the definition of steady. Take a picture now, take a picture a moment later, nothing has changed. ddt of what's inside the control volume is constant. So that term goes away. What about the flux term? Well, we have a single inlet and a single outlet. So we have this integral over the control surface of rho v dot n dA. Okay, the only place where there's flux happening is at the inlet and at the outlet. So we've got something really that looks like that. Let's sketch a possible scenario here for what we've got. We've got a control volume that may look like that. Okay, here's an outlet, here's an inlet, stuff coming in there, stuff going out there. I'm going to call that plane 1, I'm going to call that plane 2. And I have properties that are uniform at plane 1 equal to V1 rho 1. And the inlet has an area A1 and the outlet has an area A2 with a speed V2 and a density rho 2. So therefore that term is equal to the integral over region 1 of the same integrand plus the integral over region 2 of that same integrand as well, right? Because we only have one inlet and one outlet. In region 1, this region right here, V dot n, V points in, N points out, N points out. In region 1, V and N point in opposite directions, so that term is going to be negative. It's going to be equal to minus V1. Rho 1 is uniform across the entire surface, so when I integrate over the surface, it's just a constant. I can pull it out. So I've got the integral of rho 1, I've got rho 1 times the integral over surface 1 of, minus V1 dA. Similarly, for region 2, I've got the rho 2 times the integral over region 2 of plus V2 now, because V dot n is equal to plus the magnitude of V2 in this case times dA. Both V1 is uniform across the whole of A1 and V2 is uniform across the whole of A2, so I can pull them out of the integral and the integral becomes very simple. I got minus rho 1 V1 A1 in this case, and in the case of the outlet I've got rho 2 V2 A2. Notice the plus right there. Okay, so putting it all together then, what I've got is 0 is equal to 0 minus rho 1 V1 A1 plus rho 2 V2 A2, or rho 1 V1 A1 is equal to rho 2 V2 A2, the form that we're used to seeing for continuity is in fact recovered. Finally, just to wrap this up, I could have gone straight to my RTT form number 1, the restricted form, and express the same result, right? Because I made the assumption that this was applicable when I started. So let's do that. Let's start with this form right here and repeat the entire analysis there in kind of one shot, right? So let me just grab that quickly here. Boom, go back down. Okay, where are we? Yes, here we are. Okay, so all I'm doing here is using RTT number 1. Flow is steady, so this is 0. B1 is equal to 1. B2 is equal to 2. This is conservation of mass, so the left-hand side, which I didn't copy here, is dB cis dt, dm cis dt, and of course that's equal to 0. So in one shot, using RTT number 1 in this case, I got that rho 1 A1 V1 is equal to rho 2 A2 V2. Same result as we expected. So both methods agree. Great. Well, I'm going to stop right here to keep this video under control here a little bit, and I'm going to make another one with an example of this. So we'll call this one video 1. I hope you got something out of this and you understand conservation of mass a little bit better.